Welcome back to Chapter 5, and we are going to continue with Section 2, using perpendicular bisectors. So today we're going to use perpendicular bisectors to solve some problems. So starting into our vocabulary, our first one is a perpendicular bisector, which, if you remember, perpendicular means it creates right angles, and bisectors means it cuts it into two congruent parts. So we need both of those to be true to be a perpendicular bisector. So the definition states a segment, ray, line, or plane that is perpendicular to a segment at its midpoint. So what does that necessarily mean in a picture? So we have a segment, and we can call this segment AB, and its midpoint, AB has a midpoint at point J. So the midpoint means it's in the middle, it has two congruent sides. And the perpendicular bisector now will be a segment, ray, line, or plane that is perpendicular to the segment through that midpoint. So I'm through the midpoint and I am perpendicular. So that will be what our perpendicular bisector means. Next, we will see the word equidistant a lot in this section. So equidistant, kind of like the word says, equal distant. A point is equidistant from two figures if the point is the same distance from each figure. And again, if I'm going too fast through the vocabulary words, you can always stop it and continue writing and then push play again. Next word is called concurrent. So when three or more lines, rays, segments intersect at the same point, they are called concurrent lines, rays, or segments. So when three lines, rays, or segments intersect at the same point, those lines are called concurrent lines. And with that, the point of concurrency, so we're using now the concurrent lines with the point. So the point of concurrency is the point of intersection of the concurrent lines, rays, or segments. So notice out to the side here, I have three lines that intersect at the yellow or the orange point. So the lines are actually called our concurrent lines, and I could have rays or segments. And the orange point is called the point of concurrency, and a lot of times I will call it POC, the point of concurrency. And another new word that we will use in this section is called the circumcenter. So the point of concurrency, or the POC, of the three perpendicular bisectors of a triangle. So we're going to kind of put the perpendicular bisector into a triangle, and we're going to use the circumcenter to figure out some things with the triangle. All right, so something that we need to remember, the perpendicular bisector So the perpendicular bisectors of a triangle have the point of concurrency called the circumcenter. And that'll be important because we'll have a few different point of concurrencies that go with the next few sections. All right, moving on to our theorems for this section. So our note card number 2 for this chapter is called the perpendicular bisector theorem. So in a plane, if a point on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So point C is on the perpendicular bisector CP, because we noticed that P is the midpoint, and that line goes straight through and is 90 degrees. So CP is the perpendicular bisector of AB. Then CA is going to equal CB. And we can use that theorem in some of our problems. All right, and the second theorem for this section, but note card number 3 is going to be theorem 5.3, converse of the perpendicular bisector theorem. So we're going to kind of flip it. In a plane, if a point is equidistant from the end points of a segment, then it is on the perpendicular bisector. Of the segment. So if a point is equidistant, so since DA equals DB, so those are, notice that D is equidistant to the segment, then point D lies on the perpendicular bisector of AB. So notice that it doesn't necessarily go CP doesn't go completely through point D, but using this information, if I have all of that, then I know that that continues down straight through, so point D is actually on the perpendicular bisector. All right, so using that information, we're going to use theorem 5.2 first. So we are told that AC is the perpendicular bisector of BD. So let's mark that. I know that AC is the perpendicular, so perpendicular bisector of BD. So with that information in theorem 5.2, I know now that AB is equal to AD. So AD is equal to AB. Now I can set up my equation to start solving for x. So AD equals 4x, AB equals 7x minus 6. So if I subtract 7x over equals 7x minus 6, subtract 7x over to solve this equation algebraically, negative 3x equals negative 6. Dividing by negative 3, because I have to get x alone, x now equals 2. So, and now I need to make sure I solve for what I'm being asked to find. So AD is actually 4x. So 4 times x is 2, so now I know that AD equals 8. And what would AB equal without having to do any work? 8 also, because we also know it's equidistant. All right, so moving on to the next example, we're going to use theorem 5.3. So in the diagram, we know that KN is the perpendicular bisector of JL. So what segments lengths in the diagram are equal? So since, looking at A, since KN bisects JL, we know that NJ equals NL, which we just put because of the perpendicular bisector. Because K is on the perpendicular bisector, I now know that JK equals LK, because of that would be because of theorem 5.2. And also in the diagram, I see the same measures on those two line segments, so I know that JM is equal to LM, and they are both 13 units. All right, so I have said all of the things that I know are equal. So is point M on our perpendicular bisector? So we can use the information, because MJ and ML are equal. We know that M is equidistant from J and L. So, by the converse of the perpendicular bisector theorem, so converse of the perpendicular bisector theorem, I now know that M is on the perpendicular bisector JL. Or M is on the perpendicular bisector of JL, which is on line KM. So go ahead and stop this video and do checkpoints 1 and 2. Here are your answers for checkpoints 1 and 2. And now moving on